Greetings and welcome to our second session to organic chemistry. In this session, I'll be taking you through isomerism in organic chemistry. It has been very well explained in this session. Make sure you have where to note down and keep on pausing such that you can note down each and everything. And after this, I'll be giving you an assessment to try out, and then we can test ourselves how far we are in isomerism in organic chemistry. Let's go direct to introduction. So in this introduction, we shall be looking at what isomerism is. And we're saying that isomerism is the existence of compounds with the same molecular formula but different structures or arrangements of atoms. So that's existence of different compounds with the same molecular formula, but they have different structures or arrangements of the atoms is what you call isomerism. And those compounds, we call them isomers. And we're saying that isomers are compounds with the same molecular formula, but different structures. So those compounds which are formed as a result of isomerism, those are the ones we are calling isomers. And we're saying the importance of all this, it helps to explain why same formula gives different compounds. You have the same formula, but you are seeing different compounds with different names. What brings that? What brings that is what you call isomerism. Let's dive into the different types of isomerism. We have two major types of isomerism, where we're saying the first one is structural isomerism, and the second we're saying it is geometrical isomerism. And we're saying that in geometrical isomerism, we have the cis and trans. We shall be able to know what does cis mean, what does trans mean, looking at even examples of a compound which exhibits cis and the one which exhibits trans. And we are saying that in structural isomerism, atoms are connected differently. Already we have said that isomerism existence of compounds with the same molecular formula, but they're having different structure. Now, when we have these two types, and we're saying that in structural isomerism, these atoms, they are connected differently. We have a number of structural isomerisms which we are going to look at. The different types of structural isomerisms, and also we look at how each type can be explained, looking at different examples under the structural isomerism. Then in geometrical, we shall look at those which have cis and those which have trans geometrical isomerism. We're saying that in cis and trans isomerism, they have the same connectivity, but different arrangement in space, just in space. They have the same connectivity, but different arrangement in space. Let's dive direct to the structural isomerism. We have three types of structural isomerism. We have already seen that in structural isomerism, atoms are attached differently. Now, we have those where the atoms are arranged in chain. They form different carbon chains, and that one we call chain isomerism. Then those ones which have functional group at different positions, we call those ones position isomerism. So in position isomerism, we say is the existence of compounds with the same molecular formula, but they differ at the position of the functional group. Or they have the same molecular formula, but with different position of their functional groups. That is what we call position isomerism. Then we have the functional group isomerism, from the word functional group. This one, they are saying they have the same atoms but different functional groups. They have same atoms, but the functional groups are different. Maybe you find that it has carbon, hydrogen, and oxygen. But when you look at the functional group that they are having, you find that they are different. We shall look at each one of these. We are going to look at the chain isomerism, examples of chain isomerism, examples of position isomerism, and functional group isomerism. So we shall be able to understand how can we see this, that they have the same atoms, but they have different functional groups. Let's have a look at this first type of structural isomerism. The first type of structural isomerism, we are calling it the chain, which we have already seen. And we have seen in their chain, they exhibit different chains. We have seen that in here, that the different carbon chain, they exhibit different carbon chain. And that's what we are looking at here in chain isomerism. We are taking an example. The molecular formula is C4. We have C4H10. So these are how many carbon atoms? 4 carbon atoms and 10 hydrogen atoms. And now we are looking at isomers, the compounds which have the same molecular formula, but they have different structures. So which isomers can we get from this molecular formula, C4H10? How do we get that? The first thing we need to identify, what is the functional group? Which group of organic compound does this one belong to? In our first session, for those who have not watched the first session, we are looking at all that, the nomenclature, how we identify functional group. If you have not yet watched that, please check on our first session and you'll be able to see all that. But when we see 4 carbon atoms and the 10 hydrogen atoms, we automatically see that this one belongs to this group, CnH2n plus 2, where n is 4. 2 times 4 is 8, plus 2, 10. Do you know the group of organic compounds which have this group general formula? That's what we call the alkanes. So in here we have alkanes, and we know that alkanes, they have the functional group of single carbon to carbon bond. So that's what they have in common. So let's see. They have given us the first example as butane, and butane is a straight what? Chain. While we have another group which is 2-methyl propane, which is a branched chain. So we can just have their structure. Number 1, even if they have not given us these names, we can be able to generate them by ourselves by using this format that we have started with. We already have the molecular formula. We see where is it originating from, what is the functional group. So we see that it has 4 carbon atoms, 1, 2, 3, and 4. Now, the functional group is single bond. So which means this is okay now. They have all single carbon to carbon bond. And then thereafter, we can include our hydrogen. We know that carbon can accommodate a maximum of 4 bonds. And you can see this carbon here. It has 1, 2, 3, 4. Let's also satisfy this. It will have 1, have 2, we have 3. When you count the total number of bonds, we have 1, 2, 3, 4. Good. We go to the next. It already has 2, and therefore we can add the other 2 bonds, and then it comes 1, 2, 3, 4. Then this one also, we satisfy it. In our first session, we were able to see how we can name such compounds, and if you look at it, having 1, 2, 3, 4, those are 4 carbon atoms, and we said such carbon, those compounds of alkane with 4 carbon atoms, we have a prefix of but. because it is an alkane and therefore it becomes butane. So that's why we said it can be our first isomer. But now we want to look for the second isomer, which is, they have already given it once, but we said even if you don't have, you can still find it. Here we have 1, 2, 3, 4 carbon atoms, which means we can remove one and we make it a blanche. So this becomes 1 carbon atom, 2 carbon atoms, 3 carbon atoms, and then one of those we can make it a blanche. So when it becomes a blanche, then we satisfy all these ones again by putting the hydrogen atoms. This is 1, 2, 3, 4 bonds. This one has 1, 2, 3, which means he's missing only one. Then this one has only one bond, then we add the remaining, which are 3. Then this one has only one, we also add for it the remaining. Okay. Now, so which one is the remaining one? It becomes this and that. So those one become how many? 4. So in a count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogen atoms and 1, 2, 3, 4 carbon atoms. So when you're naming, we say that we can number from the functional group, but you know that the functional group of alkane is a single bond. So whether we start from here, we can start from here. This is 2, 3. Or we can start from this side. This is carbon 1, carbon 2. This is carbon 3. So whether we start from this side or we start from the other side, we see that our blanche, which is the methyl group, is on the second carbon atom. That's why we can say this is a 2-methyl. The parent name is 1, 2, 3, the propane. So we say 2-methyl propane. Now, why are we saying this one belongs to the chain isomerism? We say that in chain isomerism, they exhibit different chain. They have the same molecular formula, like now here we have C4H10, but they have different chains. This is a straight chain. This one has a straight chain. And then this one has a blanched chain. This is blanched chain. So that's the one which explains to us the chain isomerism. Let's look at the second one, which is the position isomerism. And we are considering, in the position isomerism, we are considering the molecular formula of this. Here it is C3H7, and then we have OH. Which group of organic compounds has the functional group OH? We run very fast to the alkanos, or what you call the alcohols. So, since we know that all alcohols, they have OH as one of their functional groups, and then we have 3 carbon atoms, which means we can come and we distribute 3 carbon atoms, and then we include our functional group. That is the first one. Let's also try another one. We have 3 carbon atoms. Then we can have functional group on another carbon atom, like here. We can have it at that point. Then after we distribute the remaining hydrogen atoms. This one needs 4 bonds for it to be stable, so it has already 4 now. This one has 2, so we add 2 hydrogen atoms. This one has 1, so we add the remaining ones. And then we can give it the name. Then we have also this. Let's do the same. For it needs only 1 hydrogen, because you can see it already has 3, and therefore it needs only 1 bond. And we join it with hydrogen. We have that, and also this carbon, we make it complete with hydrogen atoms. If you count, does it give us the same molecular formula? Let's count the hydrogen atoms. We have 1, 2, 3, 4, 5, 6, 7. 7. How many carbon atoms? 3. With the OH, which is our functional group. What about here? We have 1, 2, 3, 4, 5, 6, 7. Good. So they all have the same molecular formula. But what is the difference? They have their difference is the position of the functional group. That's why we call them position isomerism. And therefore the isomers, their difference is the position of the functional group. So we can see they all have the propan, prop as our prefix. But because they are alcohols, they become propanol. But now this one is on carbon 1. This is carbon 2, carbon 3. This is carbon 1, carbon 2, carbon 3. So you can see the functional group in the first is on carbon 1. So we can call that one propan 1 ol. Are you seeing that? Then this one, it is on carbon 2. So you say propan 2 ol. So you can see that that one becomes our very good answer, showing the position isomerism. Then hope that we are moving together and we are understanding the difference between the chain isomerism and the difference between the position isomerism. And now let's look at the functional group isomerism. We have that example, which is C2. We are considering C2H6O. Okay, and we are saying that we can have different isomers where we have 2 carbon atoms with O. We can have the ethanol. We can also have an ether. Let's draw their structures. For ethanol, ethanol is written as CH3 CH2OH. Does it give us the same molecular formula? Let's see. 2 carbon atoms, good. 3 hydrogen atoms, 5, 6, good. 1 oxygen atom, very okay. Are you seeing that? What about ether, dimethyl? Dimethyl, which means there are two methyl groups, and we know that the functional group of ether. The functional group of ether, we looked at it yesterday, it is that O with bonds attached to different alkyl groups. So if you are talking about methyl, which means it becomes CH3 or CH3. I think so. The difference is the functional group. Here the functional group is OH, and here the functional group is O for ether. For these alcohols, it is OH, while here it is O. So this is our functional group. If you look at this, this is ethanol having the molecular formula C2H6O, and here this is diethyl ether. Or we can call it methoxy-methane. Methoxy-methane. When you go back their side on the naming, the session we had, you'll find there how all these names come about. Don't you think we are done with structural isomerism? Because we saw that structural isomerism is divided into 3. We looked at chain isomerism, we looked at position isomerism, and now we have looked at the functional group isomerism. That is done. We say that we have only 2 types of isomerism, structural and then geometrical. Geometrical isomerism. And therefore, since we are done with structural isomerism, can we dive into geometrical isomerism? Here it is. Geometrical isomerism. We are saying that it occurs in alkenes restricted on rotation around carbon-to-carbon double bond. That is the geometrical isomerism. Strictly found in alkenes, and it happens due to the rotation around the carbon-to-carbon double bond. Let's look at, we say that it is divided into the cis form. We have cis form and the trans form. We are going to have a look at all those. Now, in cis form, groups are on the same side, while in trans form, groups are on opposite side. For example, in but2-in, but2-in, which means it is but is a prefix for 4 carbon atoms, but in, it shows that this is a double bond, but a double bond on carbon 2, so which means we put our double bond there. Put our double bond there. It is in between there. So we are looking at this compound. There is when the groups are on the same side and when the groups are on opposite side. So in but2-in, we can see how this group exhibits the geometrical isomerism. And now the question is, how does the but2-in exhibit the trans and cis form? The trans and cis form. I want someone there to try it out, and then you prove yourself whether you are able to get the difference between the cis and trans form of but2-in. I want you to draw those ones, and you tell me, how do we draw those ones? Showing the cis and the trans of but2-in. The cis and the trans of but2-in. So we are going to start with trans, and then I believe now you can mark yourself. Trans. In a trans, we are saying that the groups are on opposite side. So if we are to write butene just as butene, which means here you have hydrogen 1, 2, 3, we have hydrogen atom, here we have hydrogen, here we have hydrogen, here we have hydrogen. Then also here we have hydrogen, here we have hydrogen, hydrogen, and then we have hydrogen. So we want to see how can we draw this one in form of trans and how can we draw this one in form of cis. So in trans, we have seen that the groups are on opposite side. Which groups are we seeing? Our function group is here, C, double bond, C. This is what I have drawn. So we have the groups attached to this carbon atom and this carbon atom. The group attached to this carbon atom is a hydrogen and methyl. Hydrogen and methyl. So if we have this hydrogen attached and then we have this CH3, for us to call it a cis, it will be when these groups, now even on this one they are the same, but when they are on the opposite side. Are you seeing that? Are you seeing that? So we have the hydrogen which are on the opposite side, and we have the methyl. Well, let's look at this. We have the methyl groups on opposite, the hydrogen group on opposite. So we call this one trans. A trans but2-in. Then how does cis look like? The cis is when they are on the same side. Cis. So in the cis, which means we'll be having carbon to carbon, and now we have the hydrogen on one side and hydrogen on one side. Then the methyl group is here and the methyl group is there. So this one we call it the cis but2-in. So in cis, these groups are on the same side. We can see hydrogen on the same side and methyl group on the same side. So that's how we can differentiate between a cis and transform in geometric isomerism. Let's move on to the importance. Why do we need isomerism? So we're saying that these isomerism are very important because it helps to explain the diversity of organic compounds. Different compounds having the same molecular formula, but their structures are different. And we have seen that actually we can have the same molecular formula, but we have different compounds coming from even different groups. We have seen where we have ethanol, and then the other side we have an ether. So we have ether and alcohol having the same molecular formula, but you see the arrangement of atoms is different. So it helps to explain the diversity of organic compounds. It also helps to determine the physical and chemical properties of different organic compounds. Then finally, it helps in industrial applications. We can be able to understand their application of different organic compounds as fuels in medicine and also in polymers. So that is the importance of this isomerism. We have some practice items. These ones, I want you to try them, and then you put your responses in the comment section. So draw all possible isomers of C5H12. Please make sure you try that, and then you put it in the comment section. Be the first one to comment. Be the first one to comment and respond to those practice items. Then number 2, distinguish between cis and trans butene. I believe from our discussion, you can be able to differentiate between the cis and trans. Then part 3 is saying state one property difference between ethanol and diethyl ether. I believe we saw that when we were discussing. So I want you to give me the difference between ethanol and diethyl ether, because they all have the same molecular formula. They have the same molecular formula. And in summary, what we have been able to discuss in today's session, we have been able to see that under isomerism, the compounds formed, we have those which the ones we call the isomers, and we say that these isomers, they have the same formula, but they have different structures. And we say that there are two main types, the structural and the geometrical. We have seen the difference in the geometrical, where we have the cis and the trans, and then in structure we saw other 3 types, where we had the chain, the position, and the functional group isomerism. Then in summary still, we have been able to look at the key to understanding complexity in organic chemistry. We have been able to understand even the importance of having the isomerism. Otherwise, I want to appreciate you for being part of us up to the end of this session. I just remain Nyirimbibi Isaac, has been taking us through. That is the WhatsApp number or telephone number you can use to reach out. If there is any concept that has been a problem to you in organic chemistry, physical chemistry, inorganic chemistry, you can drop it there or put it in the comment section, so that in our next session we can be able to tackle on that. For those who may not use WhatsApp, that is the email address that you can use to find different resources. We have different resources that we have on market. We have textbooks and other chemistry related resources. So you can use any of those details to get in touch. Don't miss out our next session. We are continuing with organic chemistry and other tutorials on physical and inorganic chemistry. If you have managed to get something in this session, don't forget to like, subscribe, comment, and share with friends, because as we said, sharing is a key. Make sure that there is someone you have shared with this content that you have learned. Otherwise, God bless.